So this video is going to cover the equations required for the free vibration topic. So I guess the first thing to consider is what the definition of free vibration is. So free vibration occurs when you have no external forces on your system. Okay, so this means that the only forces are internal to it, so things like being caused by your springs and by your dampers. Alright, so the only way that you end up with vibration in these situations is due to the initial conditions on your system. So you might have an initial velocity or initial displacement away from the equilibrium position, which causes your system to vibrate. Obviously, since you have no external forces on the system, it's not going to be able to be caused by that means. So the other alternative is forced vibration, and obviously this is when you have external forces applied. Alright, and we're going to look at that in next week's topic. So for the free vibration, usually what you're looking for is the equation that describes how your mass in your system changes or moves with time, I should say. So I'm going to go through the typical steps required for that. Okay, so typical steps to get your equation for x, how your block or your mass moves as a function of time. So the first thing that you need to do is draw the free body diagram of that mass and identify all of the different forces that are acting on it through your springs and through your dampers, and also where the mass and the acceleration are heading. The next thing you need to do is sum your forces to be equal to the mass times the acceleration, and this will give you a differential equation, which theoretically you could solve using your mathematical processes to solve ordinary differential equations. Or the way we're going to do it is a little bit simpler, in that we have equations that have already been solved. They're just general forms that you can fill in based on some other information. So it's just a little bit easier than trying to solve it from scratch. So once you have your equation for the sum of the forces is equal to the mass times the acceleration of your block, the third thing that you need to do is to solve for two things. We need the natural frequency, omega n, and the damping ratio, which is how I'm going to draw it here, which is zeta. And we can get that from a general form of our equation, because we know that x double dot plus 2 omega n times zeta x dot plus omega n squared has to be equal to the thing that looks like this, that comes out of your sum of forces equals mass times acceleration equation. Sorry, and this should have an x on the end, as you'll see in the examples. So the fourth thing that we need to do is assume the general form of our x as a function of time equation. And it's based on the damping ratio that you would have solved for in the previous step. Okay, and we'll go through each of these different options in a second. And the last thing that you need to do once you've assumed your general form is to solve for the constants within that equation based on the initial conditions. So each of these different equations, these general equations, has two constants in it. So you need at least two conditions to be able to solve for each of them. Alright, so let's quickly go through these general form of the equations, and we have four different options. Alright, so the first option, remember that each of these is based off your value for zeta, and the first one is that it's actually equal to 0. And this is undamped motion. So you're going to end up with this case anytime that your system doesn't have a damper in it. Alright, there's two different ways you can write out this equation for x as a function of time. So one of them is this. Okay, the other version, which is equivalent, you just put it into one sine wave, and this time you have a phase shift. So it doesn't matter which one you use, both of them still have two constants you need to solve for. So in the first one you need to find A and you need to find B. In the second one you need to find C and you need to find psi. So obviously you should know then the only other constant in this equation, which is your natural frequency. So the next option that you have is that your damping ratio is somewhere between 0 and 1. And this corresponds to underdamped motion. And again, we have an equation that describes how an underdamped system moves with time. And it looks like that. So again, we have two unknowns that you need to solve for, C and psi. And we know these two constants. The other one in here, omega d, is your damping frequency. And you can find that from stuff you already know, like that. Alright, so the next option that you have is that your damping ratio is just equal to 1. And this is known as critically damped. Alright, so the equation this time, a little bit simpler. Okay, again, two unknowns you need to find, A1 and A2. So your last option is when your damping ratio is greater than 1, and this is known as overdamped. And the equation that you have looks like that. Again, two unknowns you need to find, A1 and A2. These constants up the top you can solve for, again with what you already know. Like that. Okay, so they're all the different general forms of the equation that you need to assume based on your damping ratio back up here in step form 4 when you pick the general form. Okay, so just quickly down here, I'll scroll down. I've got a bit of a picture of what each of the different forms generally looks like. So you can see this blue line here corresponds to the undamped case, and because you don't have a damper, what you see is that your system is going to oscillate forever and ever, alright? And it just, yeah, looks like a pure sine or cos wave. The next option was the green line, which is your underdamped case. And what makes this one special is you can see that it oscillates about this 0 line, I guess, here. Alright, so it goes under, over, under, over, under, over until it, is damped out. So that's what makes underdamped special. The other options, critical damping is when you come down and just approach that 0 line that you're aiming for, your system's equilibrium position. And 1.5 would correspond to the overdamped case, and you can see that again you're just going to approach that final position of your system, except it's a bit slower. Okay. So that's the different options for each of the different equations for how x changes as a function of time based on your damping ratio. And we'll do a few different examples in the following videos of how to use them. See ya!